Chat, got the chat open. Okay, so I'll monitor the chat. So if a question comes up, feel free to pop it in the chat. It's a little bit smaller group than the morning session because this is a little more, this is more of a middle school and secondary high school strategy. So the specific strategy that we're going to focus on is called the work solution strategy, and I kind of lump this under HIT for reasoning. HIT being high intensity instructional techniques. So we're going to talk a little bit about it, and then kind of continuing on the cognitive part from this morning. We're gonna talk about how this strategy, where it is kind of interacting in the cognitive process of learning. So before we get into it, just a couple of things that kind of get you thinking. You've been out of school probably a week, 2 weeks. Start thinking like, how do students explain their reasoning strategy? So when you ask them to explain something, what do they do? Past the I don't know. So what are they telling you? And then what are things you do to scaffold mathematical reasoning? So just kind of start thinking about that's kind of the lens I want you to start to view the process through. So, one of the big things is core programs have, they're all kind of designed the same way, but they have inherent weaknesses. And that's where I tend to focus my work is on trying to intensify where programs are a little bit weak. And one of the areas that programs, and this is going to sound a little weird, that programs are kind of weak on is problem solving. Now, I know some of you are like, what? My whole program is based on problem solving. It's not that it's not in the program, it's how it is scaffolded and supported. And that is really the key piece. So it's definitely in there, but how do they scaffold it? That's where the programs kind of start to bottleneck a little bit. There's some things in there, but they're not intensive enough for a lot of kids. So speaking of kids, I want to take a minute and kind of talk about learners. So, we have a lot of labels for our students, advanced, gifted, AP, college bound, remedial, learning disabilities, dyscalculia. We have sometimes color code them red and yellow. We've got a lot of labels for kids. And labels serve some purposes, but one purpose that they really are not helpful with is instructional decision making. So two kids with learning disabilities can have vastly different instructional needs. So what we want to look at are the learner characteristics. And when we kind of break it down by learner profile, we really have two kinds of learners that we are working with. We have strategic learners, and on the screen is kind of that description. And I'm not gonna read through the bullets, but basically, an indication that you have strategic learners is they are those students that will raise their hand in the middle of whatever you're doing. So whether you're teaching something or they're working with their partner or they're independent, they're going to raise their hand and say, I don't understand. So those two parts right there make a strategic learner key. They know when they're confused. Second, they will ask for help. Now, the third part of that is when you ask them, what don't you understand? The strategic learner is able to tell you in enough specificity that you can actually then help the student. So those are key pieces. Now, when it comes to reasoning in mathematics, these characteristics put them in a better position. So they can break problems down. They are flexible. So if they get stuck, they can kind of adjust and continue moving forward. And then when they really get stuck, they're able to recognize, hey, I've kind of hit a wall here. I'm not sure what's happening. And then they can tell you where they're stuck. Where the flip side of this is the non-strategic learner. So they are the opposite in many aspects when compared to the strategic learner. They don't regulate their learning. So they don't really know when they're confused. As they get older, they just say they're confused with everything. They don't ask for help, but when you see that they're confused by the look on their face and you ask them, hey, what are you confused about? We often get everything. I don't know anything. And they're just they can't break things down. They get overwhelmed, and then as they get older, they really just disengage. So there's not even a persistence piece there. You can't even say they lack persistence because they're not even engaging. So these characteristics put kids, um, learners in a disadvantage when it comes to problem solving. So these are the learners that are going to need more intensive types of scaffolds. Now, with that being said, this technique is excellent for all kinds of learners. Some of your strategic learners are actually already doing this on their own. But what we're going to kind of zero in now is so they've got all these other kind of bottlenecks or challenges. The piece that is cognitively is this memory piece. And this is really where this strategy is trying to help the student. So if you were in my morning session, you should have predicted that this was going to be on the next slide. This is the the picture that really drives a lot of how I look at learning and how we put in supports in places. But I break learning up into the front end and the back end. Now I'm oversimplifying the progression, but basically you learn something and then you're trying to remember it, front end and back end. So the cognitive process, this is what we are trying to tap into as a teacher. We're trying to change this. And we're trying to change it in a way where it is allowing kids to access the content, learn the content, and then retain the content. And within the cognitive process, there's different parts that are being used at different parts of learning. So in the front end of learning, and this is really where this strategy is designed to be used. However, there's certainly some applications on the back end. But in when kids are trying to learn something new, so this is when you're teaching them something new, the two parts of the cognitive process that tend to take the bulk of the responsibility for learning first is going to be the sensory registry. So that's how kids take information in. Now I say kids, this is how we all take information in. So the sensory registry, the way we learn and what you're doing right now is the way you're taking this information in that we're talking about here is your hearing and your seeing. That is how 90 to 95% of learning is happening, especially in the high school math class. In elementary, we will often be able to use manipulatives. So now they're hearing, seeing, and then they're moving things. So the three of those are kind of happening all at once, and that's how they take the information in. Manipulatives fade away in part because our math becomes a little bit too complex to model concretely. So now we're using more of a pictorial representation, generally in the form of graphing. So that happens in a couple of seconds. So you're taking in this information. So as you're taking in what we're talking about, you are funneling it, so to speak, into the working memory, short-term memory part of your brain. So this is what is being used in the moment you're trying to learn something. Now we're talking about math here, but this is anything. You've just received some type of direction, instruction, whether it's from a teacher or a peer. That information has been taken in. Now you're grappling with it. So the working memory is really the oven in the learning process. It's where the cookies are made. So as kids take this information in, they're grappling with it. So they're trying to make sense of it. And they're doing a couple of things. They're trying to connect it to previously learned content. That's where that retention piece is a big part of initial learning, because if they can't connect it, then they learn it in isolation. And when you learn something in isolation, you're going to learn it less deeper and you will forget it faster. And then it's a harder recovery. But when you're linking the information, now you're building these schemas that allow for a deeper and a longer learning. So as they're grappling with it, one of the things, and this is where this strategy is going to come into play, working memory is very limited. And what I mean by that is it can only handle so much information at one time. And once it gets overloaded, learning kind of comes to a screeching halt. And everything eats up working memory. One of the biggest um, activities or tasks that really is a drain on working memory at the high school level is taking notes. So if you're teaching and the expectation is that the kids are taking notes as you're teaching, you just have to recognize that they're using almost all of their working memory on taking the notes. They're not really processing anything to any deep level. So, one of the keys with helping kids in the initial learning is to set up instructional scaffolds that do something to help with sensory registry, take in the information, and then help offload the working memory. So with the sensory registry, generally the way that you help kids in that piece is that you organize the information. So graphic organizers, anchor charts, concept maps, steps, lists, guided notes, all of that is trying to help the kids take the information in. Now, once it gets into working memory, the way you help kids at this point is you do something in the form of a scaffold to offload some part of it so they have more capacity to process what's happening. So, when we get into upper level math, we are looking at multifaceted tasks that are requiring students to simultaneously blend vocabulary, computation, um, uh, procedural information on top of interpretation. What does this mean? And it's a bottleneck. It's very much like reading comprehension. There's a lot happening in reading comprehension. So as kids are grappling with information, they start to learn it. Now, as they learn it, it's being moved out of the working short-term memory into the long-term memory. So now we're on the back end. So the fancy word for learning is encoding. So when you learn something, it becomes encoded as a schema in your part of your brain that houses memory. So it's a memory. So in the morning session, we talked about techniques to help kids keep information accessible. Uh, that is for the back end. What we're going to focus on is, okay, so we've got these kids. They're in upper middle school, high school. If they're struggling, they more than likely are not fluent on their facts. So they're taking some of their working memory to do facts. Maybe we give them a calculator. You give them a table. That's still eating their working memory up. So, all right, well, what are we going to do with these kids when we've got to get them access to this upper level multifaceted concepts and tasks? So that's where this technique is going to come into play. So the work solution strategy is specifically designed to offload working memory so that kids can better engage in the task. So that's the whole purpose of this. So when you give a scaffold, if it's reducing some part of the task, then it is offloading the working memory, so it frees up the capacity. So that's what I want you to think about. So this is a technique that frees up more short-term working memory capacity so that they can better focus on the reasoning piece. So a good scaffold reduces something so that kids have more processing capacity to focus on. And that's where we're going to get into. Now, at the upper level math and kind of algebra is where a lot of this research is done. Research has now been kind of pushed down into the upper elementary grade levels and above into the college level. So we need kids to be, our whole focus is getting kids to algebra. That's the keystone. That's what that's evaluating. Because there's a lot of positive post-secondary things that are attached to how successful you are in algebra. Now, that's a whole nother argument if that's the right thing to do or not, but that's kind of the situation we're in. So we need kids to have conceptual understanding, some fluency built in there, factual knowledge, vocabulary, symbol notation, problem solving skills, which includes interpretation. So one of the things that, and this is where we're going to really drive into, is kids that struggle in math tend to have greater limits in their working memory. So they're already at a disadvantage because they have these learner characteristics that kind of make their thinking a little broken and bottlenecks. On top of that, they tend to have limits in their working memory. So you might have heard this called executive functioning challenges. That's kind of the broad umbrella. And there's a lot of things in there, but part of that is working memory. So one of the things that I really like to do before I get into this strategy is when I'm working with math teachers, especially at the secondary level, we have got to remember the reason we became secondary math teachers is we figured out the math and we're good at it. So our working memory is not getting loaded to the point where it bottlenecks and shuts down. Where the kids we're working with, they're not good in math, they're struggling in math, and everything is a huge task, a giant hill for the kids to climb. So I'm going to do a little working memory test here. Now, this is just a pseudo working memory test. It's going to have to be the honor system here. So have something to write or type with, a little piece of scratch paper. I'm going to read some numbers. When I'm done saying the numbers, you have to write them down in the order that I said them. So that means nobody's writing until I tell you to write. So pencils down, hands off the keyboard. I'll give you the first set, and then I'll say go, and then you write them down. So the first set of numbers that I want you to try to hold in your working memory and then write down are 38, 17, 82. Go ahead. Now we're doing the honor system because I can't monitor this, but that should have been long enough. So hopefully everybody wrote down 38, 17, and 82. So if you were able to hold those in your working memory and write them down, that means I did not eclipse your capacity and working memory. Here's the next set. So pencil down, hands off the screen, focus. I'm going to say these numbers and I'll say go, and then write them down. 30, 11, 83, 3, 27. Go ahead. Now I can't see your faces, but usually this is where people don't that we lose eye contact because things starts to get a little touchy here. So let's see how you did. Here are the numbers. I'll throw them up on the screen. 30, 11, 83, 3, and 27. Now, generally, when I do this with a group of teachers, I lose about a third of you. So there were a third of you that could not remember all the numbers. Some of you might have even wrote down a number I didn't even say. So this is another important part of working memory is it's not cumulative. So once it gets overloaded, you lose everything. All right, now we got one more set to go here. So pencils down, hands off your keyboard. Really, really focus on this one. All right, here we go. Breathe. Take some peppermint candy, stand up at a vertical whiteboard, get on a treadmill. None of that's going to help working memory. It is innate capacity. Here we go. 35, 10, 88, 9, 22, 64, 90. Go ahead. All right. Now, I'm again, when I do this face to face, there's usually a good third of the group, they just stop. They just don't even try. They sit there, don't even try. And I always tell teachers, how many times did kids in the day did you turn around and say, would you just try? Well, part of it is working memory. Now, if you got it right, throw it in the chat. This is pretty big group, so there might have been somebody that got off all right. Carrie, you're the honest one. He's lost me. So we got maybe one person that got it right. Usually I'll have one or two every once in a while. But here we go. Let's see how we did. I guess I should put the answers up before I ask if you got it right or wrong. 35, 10, 88, 9, 22, 64, and 90. And I see Janisa, I don't know if I'm saying that right. You wrote down numbers I didn't even say. Were you not listening to me? I told you what to remember. So this is great, and I'm just playing. Once working memory gets overloaded, it goes all to heck. So now, did any of you maybe remember the first number I said and the last number I said? That's called primacy recency effect. We tend to remember the first thing we hear and the last thing we hear. Now, why am I doing this? The point that I'm trying to make here is that everybody's working memory is limited. Kids that struggle in math are even more limited. So this is something to keep in mind because I gave you 3 pieces of information, 5 pieces, and 7. When you start looking at the math we're having kids do in upper, middle, and high school, it's way over 7 pieces of information. Think about how many things are involved in solving a system of equations, solving a system of inequalities, completing the square, a geometric proof, you name it. So working memory is a major challenge, not just for the kids, but for us as the teacher. How can we get this multifaceted tasks in a way that kids can access it? Because you're all experiencing what I experienced when I was a high school teacher, which is you got a group of kids that they're not even trying because for many, many years they just couldn't access it. So the whole point of this strategy is a cognitively based technique. It is trying to reduce the working memory load. So what it is doing, it is specifically designed to help kids that can't break down steps, get overloaded, have limits in their working memory, have poor computation, and it's trying to buffer those so that kids can at least engage in kind of this reasoning piece. All right, no more tests, no more numbers, but go home and give that little working memory test to your partners and see how they do. All right, so the algebraic reasoning, the work solutions. Now, I've been doing this research has been around for quite some time, and I've been working with a lot of teachers. Initially, it was very, very counterintuitive to high school teachers. More and more, it's starting to become more intuitive. Like more people are doing this naturally, or they're recognizing they're doing elements of this. And I really think technology is kind of helping this move forward. But it is a scaffold. It's a combination of a task and a material, which that's not really important to know, but it's something you're gonna do in an activity to enhance the learning with the focus on reasoning. So this research was initially started in practice. So researchers said, is there a way that we can improve practice based on what we know about working memory? So what I just demonstrated to you is that we all have limits in our working memory. Kids that have difficulties in math have greater limits. If you throw in kids with learning disabilities, ADHD, dyscalculia, you really are really getting into a profile of a learner that executive functioning is really creating challenges. So what they decided to do is they said, okay, let's set up a study where we have kids, one group of kids doing traditional practice. So in math, traditional practice is here's some problems, solve them. 1 to 10 odd, 1 to 10 even, 1 to 10 all. Whatever it is, solve the problems. Well, with the comparison group was this work solution practice where they alternated a work solution in every other problem. So every other problem was solved for the kids, and the kids were told, study this solution, it will help you solve the next problem. Now I know some of you are, I know you've got some questions popping in your head. Just hang on, we'll get to that. And you're spot on with what you're thinking. And what they found was that embedding a worked example in a practice in an alternating format produced better learning than just straight practice. So the whole idea of this is you want to get kids to interact with a fully solved problem that you provided them. And the focus is going to be on, well, what happened? That's the procedural piece. And then why in an alternating fashion. Now, initially, this was done in homework, but there is a lot of problems if you try to send this home with homework. One of them is the kids skip it. So these now, the research now is moving it more into class activities where you can kind of have a little bit more control over it. So again, traditional homework, solve problems on page 155, 1 to 21. Here they are. So the kids have to solve the problems. Traditional practice. Compared to where every other problem was solved. Now these are typed. The examples I'm using, you don't have to have, these can be handwritten. So in the work solution, the kids were given this kind of solution, and then it was followed by an unsolved problem. And they were told, look at this one, go through it, and that will help you solve the next one. So the kids started saying, okay, well, what do we do here? Well, let's see. We have what are we doing in this problem? Well, we have parallel lines cut by a transversal. Okay, so there's some angle relationships I probably need to pay attention to. And I have to find the values of X and Y. So um, there's some angles here. I'm probably going to be working with degrees and probably set up equations. So what did they do first? Well, they added 4x plus 2x equals 180. Well, why did they do that? Well, let's see, 4x and 2x, they're supplementary, they're an angle pair. So if you add them together, they equal 180. So that is what this technique is designed to do, is get the kids engaged in explaining. So what that did is it removed calculation from the task. It also removed the kids trying to figure out what to do, and it gave them an opportunity to see and explain. So this is a key. Now, some of you might think, well, isn't that the notes? Well, that's why I said what I said at the beginning. When kids are handwriting their notes, they're literally not processing anything. On top of that, their notes are often incomplete and wrong. So the whole design of this work solution is that it turns the kids into the storyteller instead of us. We're often the storyteller. We're telling them what to happen and then they practice it. And it's removing computation. It's removing what do I have to do. So removing means you've reduced the cognitive load. So now they have more left to kind of think about why it was done that way. Now we'll get into a little bit more, but that's the gist of the strategy, is that you want to give the kids a fully solved problem, give them an opportunity to interact with it, asking them like, what's happening here? Why do you think they did it this way? And there's a lot of nuances that for the questioning that come into play. But again, I just want to drive the point home that there have been now about 55 studies, and they're growing in classrooms with kids. Previous to the 55, a lot of the studies were done at university labs, it's important to know that, but university labs will often have a sample of participants that are in college. And we are not necessarily working with kids that are going to go to college. So it's a skewed sample. But now we've got 55 studies done in classrooms, and they're all basically showing us the same thing. So again, one group had just practice problems, unsolved. The other group had the same number of problems, but 5 were solved, 5 were unsolved. So if you start thinking about this, what I'm telling you was when they do these studies, you had some kids practicing 10 problems, solving 10 problems, and you had this other group, 5 were already solved for them, and they only solved 5, but they produced better learning. So this is the juggernaut when I work with teachers. It's incorrect to think that work solution group only practice 5 problems. They actually practice 10, but 5 were scaffolded practice, 5 were not. So when you study a worked example, it is a form of practice. It's just guided. Now, I'll share a personal experience. When I have a math degree, and when I was taking all these upper level math classes, I was not like a genius math person. Like I had to study. I had to go to class, I had to listen to what the professor said, I had to maybe go see him in office hours, and then I had to study. Well, one of the ways that I studied was I would find every worked out problem that professor did in the classes leading up to the test, and then I would sit there and I would study them. What are we doing here? And then once I thought I understood them, I would cover it up, and then I would try to solve it. And if I got stuck, I would look back. And I don't know if anyone else had to study like that. That is how I studied, and that is what this strategy is doing. It's forcing the kids into a task where the goal isn't to solve the problem, but it's to reason through it and then solve the next one. If they get stuck on the next one, they can look back to the first one. So this is where this technique, where some strategic learners are kind of already doing this. So as you're thinking about what was happening, what I want you to kind of think about is, why does giving kids a worked out example and interact with it produce better learning? And the cognitive process that the work solution is tapping into is, when you give the kids the worked example, you're reducing the load on their working memory. So they have more capacity to understand what is happening. So that's the first part. The second reason why it works is it gives opportunities for self-talk. So if you give kids problems to solve that are unsolved and they can't do it, they have nothing. They can look in their notes, but their notes are probably incorrect anyway. They have nothing to go from. Send it home. If the parent's not really good in math, they don't have anything. I think this is why the rise of Khan Academy and all these online platforms have come into play, because we don't give kids enough worked out examples. Textbooks have maybe 1 or 2 per lesson. I'm starting to hear maybe 3 or 4. They're almost always the simplest occurrence of the problem. So by the time the kids get to the independent, the problems are so vastly more sophisticated that those examples, they can't translate it. So the reason this works is it offloads working memory, and it helps with self-talk. So this self-talk here is an interesting piece that we kind of tapped into several schools that I'm working with. And it all depends on how you do the activity, but kids will start talking to one another about the math. And I think that in itself is big. But the reason it works is that the scaffold offloads the working memory, and it frees up short-term working memory capacity to kind of try to understand the process. It really changes the task to one of solving to one of reasoning, and it's supported. So what does this look like? So just keep in mind, when you give kids a problem to solve, there's no scaffold there. Now you can say work together, we can guide them, but there's no scaffold. But when you give them a worked example, view it as a bridge from the teacher support to the independent support. And you're also teaching kids like how to self-help later on, how to look at the examples in the book, why we take notes, how to look at those notes, how to point out where you're confused. So it's really teaching kids how to help themselves learn math later on. Now, I don't want to sell this as like the end all be all fix for everything. Kids, once they get to high school, it's hard to get them to re-engage. But again, what you're going to do is you're going to provide the solution. Now these are typed just because I've typed them over the years. Most teachers, when they start this, they handwrite them. I've worked with some schools that they are using iPads, and I'm really liking iPads with the stylus with this technique because kids are taking notes as they're going through it. They're circling. It's kind of back to the paper and pencil a little bit. Maybe I'm old school, but they're actually writing, and you can't really do that on like a Google or a Chromebook unless you have the screen that they can write on. So you give the solution to the kids, and then the problem that follows it will be similar and unsolved. And you're going to want to kind of have the kids say, so what's happening here? So the what is what they see. So what I see here is why I added 4x and 2x equals 180. So that's the what. Then every what is kind of followed by a why. Well, why did they do that? Well, these are parallel lines. That's a transversal. These are supplementary angles. Therefore, they sum to 180. So that's why I was able to set them up and add them together. You might also throw in a question, well, is there a different way to do it? Well, let's see. There's these two angles here. They have a relationship that they're equal. So I could have set them equal, but then I have two variables, so I can't do that. So these are the kinds of things that we're trying to get the kids to focus on, the what and the why. So again, the what is what they're seeing. The why is why they allow them. Now, there can be levels of why in terms of what you do. So here, a good example here is the step 1 to step 2. So what happened from step 1 to step 2? Okay, well, they added like terms. Okay, that's correct. That's what allowed them to add 4x and 2x is their like terms. You got to go another level deeper. Why? Well, why did you do that? That's where you want the kids to say, well, they will struggle with this. Why did I do that? Oh, I have to solve the variable, so I've got to solve for a variable, so I've got to combine all the like terms and get my variable with the lead coefficient of 1. So there's two levels there. So you got to know your math here, and you have to think about these questions before you try this strategy. So there's a little bit of a learning curve with teachers. But that's the idea. And you kind of just, so what happened next? Oh, I divided, let's see, what did they do there? They divided 6 by both sides. Why did they do that? Well, I'm isolating my variable. I got to get a lead coefficient of 1. All right, why is there degrees? Oh, because we're working with angles with parallel lines and transversal. Okay. Does x equal 30 kind of make sense? Well, does that make sense? Well, 2 times 30, 60, 4 to 1. Yeah, that makes sense. It's a supplement. So these are the questions. Now, what you're doing is, again, you're reducing the cognitive load because kids aren't trying to solve it. They're more talking about it. So the what and the why. So every what is followed by a why. So you get in the habit of what, why. This is changing you from the storyteller to the questioner. What is happening? Why? Now, ultimately, initially, you have to really be controlling this with the kids or they skip stuff. Ultimately, once they get good at this, it becomes a peer-to-peer activity where they're talking to one another. That's the ultimate goal, but it takes a little bit of time to get there. Now, if you are teaching with advanced kids, you can get there a lot faster. So again, offloads helps with self-talk. Now, how do you design these? There's really 3 considerations that you have to take into account. Some of you are probably thinking about some of these in that example I just showed you. So the first one is like how much guidance. So how specific the steps are broken down. So if you think back, I did not show dividing 6 from both sides. I'm sure there's some of you in this session where like, oh, I think I would have to like actually show divided by 6. That's perfectly fine. You use your professional judgment and your knowledge of the kids to decide the steps. Something that's kind of, if you've been with me a long time, if you've been in other sessions with me going back several years, there were some of the studies that did annotations. They actually wrote down why. And more recent studies are showing the annotations can actually be detrimental. So now the kids are having to read. So it reloads their working memory. makes it less effective. So if I'm working with struggling kids, I'm probably going to limit any type of annotation or writing. It's going to be more of a verbal kind of conversation, at least initially. You can fade examples. The question that the biggest gray area is the variability. Like how similar do the two problems have to be? I'll talk a little bit about that, but rule of thumb is the more challenged the learner is, the more similar they have to be. You've got a lot more flexibility with the different types of learners, which is really important. If you're noticing, I'm differentiating within the strategy. There's a lot more leeway with kids that are not struggling in math as much. So the guidance, here's the example here. So this is the one that I did. I didn't show the 6x. Here's one where I would show it. And the only thing I want to point out here is notice I made the dividing by 6 on both sides a separate step. You got to kind of make these steps clearly delineated for the kids so that they can kind of see this. All right, I see Devin sounds like I'm confirming some of the things he's doing. I like it. We need to do this more, especially with our struggling learners. They need to see the examples and interact with them. As far as a fading, and I'm not a fan of this. I probably personally wouldn't do it this way, but some of the studies did it this way, so it's an option. You do a partial solution. And what I tend to want teachers to think about is think about what is new in the problem, what is not new. So if you think about this is probably been a while since I taught. I know it wasn't an Algebra 1 when I was teaching, but it might be an Algebra 1. It's definitely an Algebra 2. But really, the only new part of this equation is understanding that if you can rewrite this with the same base, then you can set the exponents equals. Once from that point, it's just an equation. So you can say, you know what, I'm going to give them the new step so that they have to explain it and then they can finish the rest. Or the vice versa is I'm going to make them do the first step, but I don't want them to get bogged down in the solution. That's how I would do it. Some do half solved, part solved. Again, I'm not a fan of this, but it's an option. The variability is probably the thing that you'll begin to grapple with the most. This is, you don't want to be exact all the time, but again, it has to be based on the learner. And what we're seeing is the more challenged the learner is, the more similar they have to be. So what I call this here an exact match. So it's not means the numbers are same, but what it means is the lead coefficient has the same kind of relationship. It's got a positive and a positive. So it is essentially the same match. If I made this a subtraction problem or I had a different lead coefficient relationship, now we're starting to vary it. For struggling kids, or if I'm an interventionist in small group, I'm going to make mine very matched initially. Something else I want to point out too is, and you'll start to see this more, is the columns. This works best if you use this in a column situation where the left column is solved, the right one is unsolved. The other thing that we're noticing is teachers started to type this. Even though I said you don't have to type, they start typing it, and then they start reporting back that kids have a hard time when it's all typed, seeing where the problem is and where the solution starts. So if you're going to type it, do something like this teacher did, which is different colors or different font. But the handwriting is fine. I'm actually almost thinking seeing handwriting, the kids can tune into that a little better than type, but these are up to you. The variability is what you'll struggle with the most. All right, so those are the three considerations. So essentially, kind of breaking down, we're getting pushed for time here, but I think we're fine. When you break down, there's three types of questions you want to ask. You want to ask some pre-questions. So the pre-questions are designed to prime the kids. So before they even see the solution, you're going to want to ask them a couple of questions. So in my example with the parallel and the transversal, I might lead with, hey, we're going to do a work solution activity today. We've been working on parallel lines and transversals. What are some things that we need to know? So you're trying to get the kids prime. So, oh, there's angle relationships. They could be equal. They could be supplementary. And you're talking about it to prime them. It's very similar to when an elementary teacher shows the kids a book. Say, hey, we're going to read this book. Here's the cover and the title. What do you think this book is about? So they're brainstorming. They're priming. This pre-questioning is very important. It helps the kids. Then you get into the solution question. So that's what we've basically been talking about, the what and the why. Then at the end, you've got to ask a couple of questions about the endpoint. What does this mean? What does this tell us? I have been in so many classrooms over the last 3 or 4 years where kids are solving the problem correctly. So they're going through these multifaceted tasks, they're solving it correctly, they're getting the correct answer, and then I go up to them and say, what does that mean? And their number one answer at all levels is, well, that's the answer. Okay, you're right, that's the answer. Well, what does that mean? And then I get, well, that's a solution. Okay, that's a synonym for answer. What does it tell us? Kids, I was shocked at how many kids got the right answer, but really didn't know what they solved. So these are kind of your big questions. So examples of pre-priming questions. What are we how are we gonna be solving a problem with parallel lines and transversal? What might our answer look like? Hey, can we estimate it? What are the things we need to know? Is there a certain strategy? So use your expertise as a math teacher to think about, what do I need to get the kids thinking about before we jump into the solution? Then you're going to get into the what and why. So just remember, every what is followed by at least a why or a how or something along those lines. And then you got other questions you might ask. Does that make sense? Is there a different way? I love asking that question when there isn't. Because kids think if you ask them, is there a different way? There must be. So these are the ones that are most critical. These you kind of fill in based on your kids and the problems you're using. Now, the ending questions. This is one I would require every teacher to, and you need to ask this even when you're not doing a work solution activity. What does this mean? What does this tell us? What does this represent? I was shocked at how kids really, even though they solved it correctly, so they had the procedural knowledge, and there's conceptual in there as well, but they didn't know what it meant. So this is a one I would really, really ask. Now, when I asked the more advanced kids this, I still got, well, that's the answer. And then I said, well, what does that tell us? They could adjust pretty quick as I probed them. As I went down the profile of learner, they really struggle with what it means. And this is not anything indicating you didn't teach it, because I guarantee you did. The issue is in traditional practice, they're just working the problem and getting to the answer and moving on. So this is the opportunity to probe them, go deeper, ask those questions. So pre-questions, like I was kind of showing you. Okay, so what do we have here? Parallel lines cut by transversal. What are things we need to know? Well, angle pairs, there's degrees, congruent, vertical, supplementary. All of these different things can come into play. How might we solve it? Set up an equation. So whatever makes sense. So these are going to vary based on what you're doing. Some things you do, you're not going to have a ton of questioning just because it's not a deep thing. Then we already kind of went through the what and why questions. This is what we want the kids to do. So the other thing is this is going to tap into vocabulary. So we want kids using the correct vocabulary. Kids do not get opportunities to use vocabulary other than a math class. So there's vocabulary piece coming into play here. This is going to show you where they're getting stuck or where they have the procedure, but they don't know why they did it that way. And then at the end, what does the y equals 60 mean? Is that an angle? That's a great question here. Well, it's an angle here, but it's not an angle there. Is x equal 30 an angle? No, that is not an angle. So these are great questions. Does that make sense? So now you're wanting to kind of circle back. Well, let's see, 60 and 20 or 30 and 60 and 120 equals 1. Yeah, that makes sense. So don't rush the ending questions. Very important. So again, when you try this, these are the things you want to do in advance. All right, what are my three? And I really encourage you, jot your questions down. Jot your pre-questions, jot your what and why questions, jot your any questions. When I work with teachers and they're doing this multiple times in a day, so they teach Algebra 1 or 7th grade math multiple times in the day, and they have a work solution activity eat for 3 or 4 times, they tell me their questioning is completely different at the end of the day than at the beginning because they learn where the kids are getting stuck. Okay, Melissa, very good question here. None of the questions are visible to the kids in writing. You are going to write them down. They're your teacher notes, so to speak. We want to kind of tamp down the reading part because that can reload the working memory and defeat the purpose. So these are more of a discussion. Now, I think, again, if you look at the continuum of learners, and this is something I would do in AP with AP kids as well, with the continuum of learners, you have a lot more leeway with doing things with the top end of the learner group. So the questions and all this is what you're looking at, not the kids. So the checklist for this here is going to be right here. So this is what you're looking for putting in place. You give the solution to the kids. You've thought carefully about your pre-questions, your solution questions, your ending questions. And you've got to take a little bit of time to teach the kids. Like one barrier you're going to run into, and I'm sure some of you are thinking about this, well, your kids are just going to skip it. They will unless you are really trying to control it. So I have a couple of examples here, and when I say control, I'll explain what I mean by that. The 6 steps to doing this is you select your problem. It needs to be multi-step. Think about what your pre-questions are going to be. Solve the problem. Solve it the way you would want the kids to solve it, right? So this is where these could be a little bit teacher dependent. Like maybe I'm solving it a little bit different than other teachers. In algebra, some teachers have the kids draw the line down the middle of the equation, others don't. If you're the teacher that draws the line, then your solution would have that line drawn. And then you'd ask the kids, why is there a line in this? Well, that helps me stay organized. So some what and why questions are about organization. Then you sort of think about, okay, what am I going to ask at the end? And here is an example, and this is how I like them to be set up in columns. And when I said control, what I mean is you have the kids fold the paper in half, and they're only looking at the solution. I have been in rooms where the teacher did this exact scenario, did not fold it in half, and half the kids were skipping to this problem and trying to solve it. That's going to be your issue. Full disclosure, that's an issue in every school. The way we kind of control it is by forcing the kids to look at the solution. So they're going to look at the solution. You're going to ask your pre-questions. You're going to ask your what and why questions. Kids are going to use this solution to answer. And then your ending questions. Notice the problems here. I would not say this is an exact match because you got a square and a rectangle, but they're still matched. An exact match would be the second problem has square, but they are matched enough. So this is the one where you ask the questions. Once you go through this, then the kids open their paper. And in this one, depending on how much you're doing it, it could be the teacher asking questions again. It could be the kids partner up. It could be a small group with the teacher, or it could be with a partner, or it could be independent. It just depends on where you are on the spectrum. What I encourage teachers to do is when you initially try it, you're making this teacher supported in the second problem. So you're going to ask the same questions you did here, but as you ask, they're going to be solving it. So that could be a work solution activity. 2 problems, one solved, one unsolved. Probably take you about 10 or 15 minutes. Or you could do a 4 problem. So I like teachers to think about this in 2 and 4 problem activities. Here would be problem 3 and 4. Now notice it's still composite, it's still circles and area and stuff, but now we've got a triangle and half circle. But notice both of them match. Not exact match, but close enough. You'd have the kids fold their paper, then you would have the kids go through the questioning. And then the next problem they solve on their own. So when you're making this, your teacher set of materials are where you're writing your questions down so that you can have them, not to read them, but to keep you in line. What I really see is content knowledge of the teacher makes a difference. So high school teachers, we are more content knowledge based than maybe middle and elementary teachers. So you have to really kind of think about this in advance. Then the students are just getting the problem with the solution on it. So that is the work solution technique in a nutshell. Again, this was speed dating on the work solution. I could spend 2 or 3 days on this. But the gist of this is it's trying to get the kids to change the task from solving the problem to explaining the problem. All right, so I'll open up the questions. I think I hit all the questions that were in the chat.
I'm pretty sure you did answer them, Paul.
Whether you're giving the kids a paper and pencil paper work solution activity or it's on the computer, doesn't matter. I didn't know how I haven't had a lot of experience with schools with iPads. It worked phenomenal on the iPad. The kids had the problems on the iPad. They could move things around and large, and I think it worked out well. So I think technology is going to be another tool for these. But I don't know if anyone has any questions. Want to pop it in the chat. We're about out of time. Have you tried this in the building thinking classroom? I'm not really sure what that is. This is a scaffold that can be used in any classroom. It is a scaffold. Do you ever use color coding? I personally never got too much into the color coding. You can. I've had several students who are colorblind over the years, but you can play around with it, so I don't see why you couldn't. But yeah, any kind of arrowing, drawing, circling, I think would be fine with this. All right. Well, if no one else has any other questions, I'm glad you joined me for the last session of the day. Maybe some of you started your day with me and ended it. I'm sorry for that. I hope you have a good rest of the summer. And as you think more about this technique, just remember the entire work solution is it's a scaffold to offload working memory and support student reasoning. And it could be student to student discourse. Good. I'm glad this was a brand new strategy for some of you. It sounds like some of you are using elements of it. That's great. The whole idea of professional development is you learn something new or you get confirmation on something you've been